Today we're going to delve into a little bit more detail about grain patterns. So let's quickly review solid engines. So solid engines are where you have fuel and oxidizer mixed together and packed into a rocket, and it's solid. Once you ignite this grain, this fuel and oxidizer mixed together, it just burns until it's completely gone. So it's very hard to actually control this. It's used for very small rockets, it's used for boosters, and it's used for intercontinental ballistic missiles. Those are the common things for solid engines. If we look at your typical solid engine design, which is like you have all of this grain, this fuel and oxidizer mixed together, and it's packed into this cylinder, and you have a little hole going up the middle, it looks like this. So in the left, we show that it is just this little hole that's going all the way through. And on the right, you can see that the grain is burning, and it is causing some exhaust to come out. So the grain is the fuel and the oxidizer that's mixed together. The casing is the outer body of the rocket, and that's holding all of this stuff in there. And then the hole is where the combustion occurs. The nozzle is the thing that's basically converting all of the random motion into kinetic motion or bulk motion, which is driving the exhaust velocity, which is this exhaust. So there are some important facts about the geometry of this. So the solid fuel burns continuously. The thrust can't be controlled or can't be throttled at all. So you can't turn off the thrust or turn back on the thrust. You just have it burn continuously. But the only thing that is burning is the surface. It's just the surface of the grain. That's where the burn happens. So if you can change how much surface is exposed, then you can control the burn rate. So if there's only a tiny amount of surface showing, then you'll only get a tiny amount of burn. But if there's a huge amount of surface showing, you'll get a very large amount that is burned. You can control the thrust profile over time by controlling how the thing is burned. So let's look at this little circle one, right? The typical solid rocket engine where you have just this hole in the middle and the grain is a circle around it. And so if you look at time one, there's this very little hole that very small amount of the grain is exposed, so very small amount of mass is being burned. If you go through time, though, more grain is exposed because it's burning. And so more and more and more grain is being exposed because the hole is becoming bigger and bigger and bigger. So if you look at the thrust versus time, the thrust is actually increasing because the amount of grain that's exposed is increasing. So the amount of fuel that is burned is increasing. So if you keep looking through this for further and further times, the thrust increases over time until the very end when there's no grain left and then the rocket just stops burning. So this is what's called a progressive burn because the thrust increases with time because the grain exposure increases with time. You can also have what's called a regressive burn. That happens when you reverse it. So you have basically a solid column of grain, and then you burn from the outside in. So you start off with a lot of exposed grain on the outside, and then a little bit while later, you have less grain exposed, you have less grain exposed, and you have less grain exposed. So that's called a regressive burn because the thrust is decreasing with time. Model rockets, which many people have seen, have both a progressive burn and what's called a neutral burn. And if you look at the bottom of this model rocket, it looks like there's a hole that may go all the way through, but the hole actually only goes a little bit into there, and it's like a triangle shaped. Initially, that hole increases in size, so you get the thrust that increases, you get a progressive burn, but then eventually it reaches the edges and basically the entire back half of the rocket or top half of the rocket engine just has a flat plate on it and it's just burning straight up. And so that's what's called a neutral burn, because the amount of grain that's exposed just stays constant with time. It leaps off of the stand, and then it goes into a neutral burn, where you basically have the flat area that's just moving up the engine. There's lots and lots of different grain geometries, and you can really tune your engines. We talked about this flat or neutral burn where the grain is just packed in there solid. And so you basically have this flat plate that's just moving up. And that is a neutral burn. Then we talked about a progressive burn where the grain is increasing in size, or the burn area is increasing in size. A regressive burn where it's shrinking in size. And then you have sort of this weird pattern, which is like this star-shaped pattern. And that star-shaped pattern is also a neutral burn, because if you really think in detail about how this star works, the little tips of the stars are burning off at the same time that the whole star is getting bigger. And it actually makes this neutral burn, which is super cool. And the neutral burn is actually what happens in the solid rocket boosters of the space shuttle. So in summary, the grain geometry of the solid propellant engines allows the thrust to change over time. And we can make it so it's dependent on the area that is exposed. And so if we have an increasing area as a function of time, that's called a progressive burn, and the thrust is increasing during that. Or we can have something where the area is decreasing as a function of time, and that's what's called a regressive burn, and so the thrust is decreasing as a function of time. The area staying constant versus time gives you what's called a neutral burn, and so the thrust stays constant. The space shuttle boosters had a star pattern, which are this neutral burn pattern, which allowed the thrust to stay roughly constant over time.